Okay, so slide 2. So the FAIR principles, I mean, everyone has basically heard about in terms of, data sharing, making sure data, is accessible. And I think, from what Jess described earlier and, what we're trying to do in ReproNim, there is findable accessible, but, what we're talking about now in terms of the semantic markup really hit at sort of the interoperability and the reusability, right? So, how do we provide sort of unified views, of data, for information across resources, and to do that in a way that supports community standards around those elements. So next slide, slide 3. And really the goal for that is to enable large-scale analyses across data sets and enable extraction of specific cohorts for analyses. That's something that we're doing in terms of our reproducible paper that we're working on. And so, the key really is to develop standards around some of these basic elements, within the data. And Dave Keeter later on will talk a bit more about the IDM model and what we're doing in terms of annotating, bids and IDM. What I'm going to focus on next couple slides is sort of some of the basic elements within that and what we're doing in terms of trying to make those more standard. So next slide, slide 4. So one of the important aspects of any of these data sets, and you saw this, in the SchizConnect demo earlier, was the idea of data elements. And one of the issues that we've been trying to tackle is how do you actually, make these common data elements standard? How do you make them interoperable? And that is something that is not very easy. And so, as Jess described earlier, when she was talking about standardization of data elements, there really, has been very limited, standardization of data elements in a formal model. And so that's one of the things that we are trying to approach. So next slide, slide 5. And, within bids and in other data structures, there are ways to describe, for example, data elements at a very superficial level. So for example, in bids, it's just one example, you can define, some ontological term, or data element term related to a data element within the structure of the data that's being described. And there are issues with that in the sense that, it is a data element that you're describing. And next slide, slide 6. When one looks at data elements across, the number of repositories that try to catalog these, they're actually not so common. So, the NDA has over 250,000 common data elements. You go to National Library of Medicine, they have hundreds of thousands of data elements that they list. And that's really because these common data elements are describing data elements within a specific experiment. And when one changes one of the questions or changes how the response is gathered, the common data element itself changes, right? So, the common data elements themselves, from what we've been approaching, is not the level, I think, in terms of harmonization that we're looking at. So next slide. Jess had mentioned common data elements and interlex before. And so within interlex, we do carry and do allow people to enter common data elements within this framework. But again, as Jess also mentioned, we don't try to normalize common data elements. Terminologies, ontologies, we do try to harmonize and normalize within the system. But when you get to, some of the data elements, we don't. And so one of the things that we've been developing is this notion of a federated data element. So slide 8, next slide. And really what we're trying to do here is develop a model that we can instantiate within the markup to harmonize some of these common data elements. So, this first example is a simple one, around handedness, in that we want to develop, for example, a model where one can link to specific common data elements, but then, for certain types of data elements, we can extract some higher level information, in terms of handedness. Is it, right or left? No matter if it's a numeric value from an Edinburgh scale or if it's just a questionnaire where someone asks, are you right or left-handed, right? So trying to extract some of that information and place it at a higher level. Next slide, slide 9. We're also doing this with data elements that we're extracting from, for example, free surfer volumetric measurements. And again, this is something where we are defining a model that basically defines, in this case, the NIDM RDF, a representation of a data element. So we're not specifying, another sort of data element, within IntroLex. What we're doing is we're specifying a model that links to a number of attributes. And this is, what is the measurement about? So that would be the brain structure that, for example, the measurement is about, information on units, information on what type of measurement it is, and what type of data it is. What is it, the representation of the data? And so this is a model that, we're currently working on and building out. And so next slide, slide 10. And one of the important things to keep in mind when discussing common data elements and ontologies and terminologies is that terms and data elements are not the same thing, and we can potentially get into trouble when we mix them, in the sense that terminologies around age are about the concept of age, where participant age is a specific data element that has a specific connotation in terms of the study, that it's the age of the participant at the time when the data was collected, right? But they do link to one another. So participant age is, for example, a measurement of, the ontological term age. Next slide, slide 11. And so around these data element models and the terminology behind them, that's where, we're bringing in IntroLex, which is the newer platform from NeuralX, which was some older technology. So with IntroLex, we are providing the ability for the NIDM term markup. And so next slide, slide 12. So here you do have the ability to search for terms and common data elements. Within the next month or so, we'll have an updated search interface that provides a little bit better way to distinguish between terms and CDEs and other faceting capabilities around the terms. But once you do have the terms and the CDEs in the system, and so this is one of the places where, for example, the DICOM terminologies, we've been bringing them there, and also the new award that was mentioned earlier that Dave Keeter received for NIDM terminologies. This is one of the areas where we're going to collate that information as well. And then last slide, slide 13. And this is all done through the services that are provided by the system itself. And so those are the services that Dave Keeter, who's next with his slides, is working into the NIDM markup tools. So Dave, I think you're up now.
Yeah, just give me 1 second here. Sorry, switching over to slides. All right. So I might have to stop share and reshare, I guess. Reshare. And this one. Share. And what the hell happened to it? Here. There. Okay. All right. Thanks, Jeff. I just put this slide in because Sasatra skipped over it, but I'm sure many of you already know a bit about what NIDM is trying to do because you've been on the calls, or in the case of SchizConnect, you're exporting some of these NIDM files now. But NIDM is a linked data format for describing many aspects of the data lifecycle. It's the kind of overall goal. and it's separated into smaller units. There's an IBM Experiment component, which we'll sort of talk a bit about on this call, which aims to capture metadata about experiments and provide kind of a structure and model for people to describe information, essentially using linked data and semantic web principles and all the tooling that is needed to facilitate that. There's the IDM workflows models, which Satra mentioned before, but the idea is to capture the workflows of what happened to the data in a precise form, also in linked data using sort of the same semantics as an IDM experiment. And then there's the IDM results models, which are currently implemented for sort of mass univariate statistics in MRI, but as you'll see in this presentation, we're extending those to include sort of brain volume computation, and really the idea is to be able to capture outputs from any statistical model, also in the same linked data format with similar semantics, such that one can use semantic web query capabilities to search across these things. They're big graphs, and so you kind of really might only need to learn sort of one model, if you will, to get to any of these data. It also provides like a living record that humans probably shouldn't look at, but computers would like to be able to compute across these things to understand what was done to the input data to produce these results and so forth. So focused on the IDM experiment model right now, because it's kind of most applicable to what I think we'll be doing on the 18th, and what we've done a little bit with already in SchizConnect. IDM experiment model is really just a simple hierarchy of a project. Contains sessions, and sessions contain acquisitions, and the acquisitions have an entity which is more like, you can think of it as metadata or even data that was acquired, and the activities are the process that was involved. Each of these boxes here, you can add as much metadata in the form of tuples as you want according to linked data principles, and really all you have to do is say precisely what you mean. And so we have a subset of project attributes at the top. That's a DCT title, and if that's a URI or an IRI, and if you were to dereference that, it would take you out to some terminology resource that would tell you what we meant by the information that follows, and in this case it's a title or a description or a publisher or so forth. And so if you follow these basic principles, you can build up some complicated graphs where you capture metadata about, in this example, all the imaging sessions that were collected as part of various sessions as part of a project. These acquisitions could be, image acquisitions, or they could be assessment acquisitions or whatnot. These things get associated with what the provenance data model calls a person, or an agent. In this case, I'm showing people that were subjects that the data was collected on, but they could be agents. Oops, sorry, the mouse flipped. Over on the right side of the graph, there's the IDM analysis software, FreeSurfer, that is also a prov agent, but in this case, it's not a person, it's a piece of analysis software. And so with a few basic building blocks, essentially, and some principles of how you add information, you can, essentially model a lot of things. And I might argue that you can model anything this way, really. And so this particular slide shows how we're connecting, IDM experiment related information, the left box, with IDM results style information, in this case, brain volumes, in the right box. And where we're, then using some of the techniques that Jeff had talked about, linking the anatomical specifics from a particular software package, in this case, FreeSurfer, with the more generic Uberon sort of terms of, what anatomy they're referring to. So by doing this, you could essentially collect brain volume data across many software packages that maybe using different atlases, but still perform queries across these various data sets to say, as a neuroscientist, I'm just interested in amygdala volume, and I don't really care what FreeSurfer referred to it as, or what FSL referred to it as, or what Ants called it. I just want all the brain volume data about the amygdala, and then I'll look at sort of the provenance graph, the thing on the right here, and then later on say, okay, where did this amygdala volume come from? Oh, I see it came from a volume computation that's associated with the FreeSurfer software. These blue boxes and I guess it's a pink box, potentially have all kinds of metadata about what versions of this tools were run, where they were run, what computational systems they were run on, with what libraries. These single boxes could be expanded out into entire subgraphs, such as an IDM workflow record. So that's kind of the idea. And to do this sort of thing, here's a picture of an annotation workflow essentially. But to do this sort of thing, you need some tools and you need some vocabularies, terms, and ontologies to make it really useful. But also we want to make it, we want to have a pragmatic focus and make it usable by a community who doesn't care much about linked data or semantic web. They just want to do some things. And so in this graph here, we're showing some of the tools that we have created at this point, and we'll be using probably on the 18th, but still work needs to be done in all these aspects. And then so basically here in this graph, we have like a BIDS data set essentially, and this is something that you could get from SchizConnect right now, for example, where the images are formatted according to BIDS, and the assessments are formatted in their own, whatever the data, the originating system, how they formatted and refer to things. But if you take the BIDS images and you kind of use our annotation tools, what it tries to do in the BIDS data structure, for example, you have a participant.csv file that may have some variable names in it that are otherwise unannotated. What our tools attempt to do is provide you a way of annotating them using a fixed set of terms. And so what they do right now is the tools will load in the variable names, and they will go and they will search the interlex for terms that may be appropriate for your use, and they'll allow you to select a term to annotate your variables with. And if there isn't a term there, it'll allow you to add terms. What our newest grant, an IDM terms grant, will allow us to do is spend some time working on these terms, such that instead of having 25 choices for age, none of which that have units or frames of reference, that you'll have a more discrete set of age terms, all of which are hopefully used and usable by the neuroimaging community specifically, so that this kind of workflow is much easier, and you have there's less ambiguity in how you're marking up your data. But essentially our tools will then export these JSON, BIDS JSON annotation files. They'll also export an IDM experiment record, because once we've done this activity, we can make these linked data records, and these IDM experiment records, which are essentially just serializations of these IDM graphs, can live with the BIDS data structures, or could be shipped off to like the Repro store, an online graph-based database that then could be queried against. And since everything is kind of URIs in the linked data world, the data doesn't have to live where the metadata record is. And so you could think of this nice database system where these IDM records live. You query across these IDM records using the semantics and ontologies that are organizing these terms, and bring back sets of integrated data that may be applicable to your query. Hopefully they are applicable to your query, and then go off and get the data from whatever resource where they exist. This is just another picture of basically going from a original sort of DICOM imaging directory to the BIDS data structure, where we've now augmented the participants.tsv file with this sidecar, they call it in BIDS sidecar JSON file, and also inserted our IDM turtle file in there. And if you were to look into one of these participants.json files, it's pretty simple. All it is, where it's a JSON file where the key is essentially your variable name inside your original TSV file. This equally applies to CSV files or Excel spreadsheets or whatever. The key is your variable name, and the the various subdictionary essentially is information about how that variable name has been mapped to a term that lives somewhere. And we're working with Interlex because you know, we've worked with them a lot, and it's really a nice system to be able to add information, and there's a nice rich API for doing all of this programmatically. So so here's an example of, so the top left box essentially is, so what I did was I went to SchizConnect and I downloaded all FBurn phase 2 data, the imaging data, let's say. And so what I got from SchizConnect was a nice BIDS data structure of the FBurn phase 2 imaging data. And the data that comes back, this is kind of the way Kate and I did it initially, was just to say, let's just do a straight MRI to BIDS conversion, essentially, where we're not doing any kind of semantic markup, really. We're just going to just brute force convert it. And so what you end up with from SchizConnect currently is you'll see that there's these assessments where there are some variables. In this case, there's a DX variable and a study variable in the demographics information that comes back with the imaging data. And these are put into, naively put into the BIDS namespace. And that doesn't really mean anything because the BIDS vocabulary doesn't define a term DX or study. You can see some of the other terms just below it, like age and gender. Those were automatically mapped because the NIDM tools kind of say, well, if you're collecting age, here's what the definition of age is currently, because in the case of BIDS, I believe age is specified in their vocabulary. It has to be a specific way. But anyway, point is, you have a bunch of variables in the original data set. Right now, they're sort of naively mapped in the BIDS exports from SchizConnect. We can use this tool from our PyNIDM libraries called BIDS MRI to NIDM, which has this annotation capability. And what it really will do, which you'll see on the next slide, is allow you to iteratively query the Interlex and pick out some terms that may match, in this case, DX and study. And in the bottom right square or rectangle, you'll see that this has been now remapped, so that study has been mapped to an SIO term, and DX was mapped to an Interlex term for diagnosis. Idea being you can dereference these and find out precisely what was meant by those things. And so part of the new grant on IDM terms is to create a version of this kind of annotation tool that's not command line based, but more of a widget you can add to your various websites. But for now, in ReproNim, we've done a lot of work on kind of making this all kind of fit together. We have this BIDS MRI to NIDM tool. There's also a CSV to NIDM tool, which will work on any CSV files. So in that case, you can think assessments, exports of assessments. But essentially what you do is it goes through, like I said, the variable names in the columns, and it does this little query. It queries our NIDM terms ontology file, or OWL file right now. It's not really an ontology, but our OWL files right now. And then it also queries the Interlex and tries to limit the amount of terms that comes back. But currently there's a lot of noise in these returned, the terms that get returned. And oftentimes you don't find something that is usable for you. And so they have an option in this command line tool to define your own variable, or your own term, sorry. And if you define your own term, then it asks you a bunch of properties like ranges and units and things that we're interested in. Again, the NIDM terms grant is to limit and to really take a pragmatic look at the terms we have being returned for things that we know folks generally collect in neuroimaging, and to facilitate query across data sets. But here, this is more of a broad view where you could really query for anything. And if your variable name didn't bring back anything useful, you have a little choice where you can say, hey, I want to query change my query string and type in anything you want, diagnosis of subject, and that will go off and do an elastic-based search of the Interlex and bring back new CDEs. It'll bring back federated data elements if there's any that match. It'll also bring back personal data elements, and personal data elements are ones that you have created previously. And this all happens using a API key that you get from Interlex. And essentially what that does is then writes out this little JSON file that goes with your bids data set in this example. And it also produces an IDM file. And so then once you have that, those IDM files, since they're linked data files, you can use, there are a variety of query languages that you can use with linked data. This is Sparkle. You can use a Sparkle query and query these linked data files. So in the case of an example we did in ReproNim, where we've done this for Abide and ADHD 200 sites, there's lots of IDM files. There may be 40 or 50 of them, because there's maybe one for each site for each project. It doesn't have to be that way, but that's the way it is. You can load those things into a graph-based database and perform queries against them. And these queries, some people don't like the way they look. I think they look pretty nice. I mean, it says, we're gonna try to capture, study, ID, age, gender, diagnosis, a tool and a structure for brain volume altogether. And we're gonna, query the assessment instruments inside the IBM experiment record that were generated by some activity that, and we want to get from those assessment records age, diagnosis, and gender, and so forth. You can read down the query just like that. At the bottom, we're getting structures and measurement types of various brain volume measures. And so, this is a very simple query. One could think about doing much more complicated queries here, where you use an ontology to sort of map things like age or diagnosis or gender to a more federated concept that would then retrieve results from studies that measured age in a different way than what NCICB age says it should be measured, which I don't think it actually has a reference point, but that's part of the problem. Or measured gender in a different way, or something like that. So I think that's it for me.